Okay, so here we go. So this is a precipitation, meaning a solid, multiple choice question, and because it's multiple choice, the math you should be able to do could be done without a calculator. Okay, so it says M plus, so they give you the charge of this metal, has a +1 charge, and a student dissolves the chloride of the unknown metal. So maybe it's sodium chloride, maybe it's potassium chloride, maybe it's copper chloride, maybe it's lithium chloride. Those are our options down here. So in enough water to make a certain volume of solution. Then they take the solution, this metal chloride solution, and mix it with nitric acid, which causes silver chloride to precipitate, so it's a solid. So the student collects the precipitate by filtration, and then they mass it and dry it. And let's talk about the reaction. So it's, oopsies. Yep. So it's the metal chloride plus silver nitrate. Now we know the metal's +1 because they tell you plus when they write the formula. Chloride's -1, so it has to be +1. So you get the metal +1, nitrate -1, and silver chloride. Now remember, nitrates are always soluble, so this is obviously the precipitate, though it tells you, okay? And they want to know who the metal chloride is. Now, if you're trying to find out who it is, a good way to do that is by molar mass. So do you remember how to do molar mass? It's grams divided by moles. That is a way to get molar mass. So if you know grams and you know moles, you can take grams divided by moles to get molar mass. Why can't you just look it up on the periodic table? Well, you can't just look it up on the periodic table because you don't know who this is. So you can't just like start doing calculations or anything. Okay, so the nice thing we do know is we actually already know the mass of the metal chloride. It's 0.99 grams. Okay, so if we can figure out the moles of the metal chloride, we can take our grams, divide by moles, get the molar mass, and then kind of compare it to these substances down here on the periodic table. So what's a good way to get moles? Well, if you know a chemical reaction, you can do mole to mole ratios. We know how much silver chloride was produced based on these numbers. You take the mass of the silver chloride in the filter paper, you take away the filter paper because we don't care about the filter paper, and that's the mass of your precipitate, and it comes out to be 1.43 grams. All right, so this is supposed to be nice numbers. 1.43 grams of silver chloride precipitate, and they tell you its molar mass is 143 grams per mole. And for every 1 mole of silver chloride produced, 1 mole of metal chloride, silver chloride, 1 mole of metal chloride had to have reacted, right? This is stoichiometry. So here's what I do without a calculator because I'm not good with decimals. I call this 143 because 143 divided by 143 is 1. Okay, 1, but it's not really 1, right? You got to go backwards 2 spots. It's 0.01. Okay. So 90, and then times 1 divided by 1, so it's still the same number. So 99.99, excuse me, divided by, now I'm going to write this as a fraction because, like I said, I'm not good at decimals, 1 over 100, which is the same as, sorry, I'm going to have to do this over here, 0.99 times 100 over 1. So it's 99 grams per mole. So you go and you add all these guys up and figure out who's the closest to 99 grams per mole. So we pull up our periodic table. I think sodium chloride was the first option. So sodium's like 23 plus chloride is 35-ish. So that's like 58-ish. Okay. I think the next one was potassium chloride. Potassium is 39-ish plus chlorine is 35-ish. That's like 74, 75-ish. The next option is copper chloride, so that's like 63-ish plus 35-ish. That's like 98. Oh, wow, that's really close to 99. It's copper chloride. You can go ahead and look at lithium. Lithium is like 7. Chlorine is 35, so that's not 99. So Our substance is copper 1 chloride. Any questions on how I did this? Okay. Another question, this is a very conceptual question. Again, that box means an arrow. So a student wants to determine the concentration of lead nitrate. They want to know, oh, I guess I didn't give myself the ability to draw on this. They want to know the concentration of lead 2 nitrate. So what they do is they react it with excess sodium carbonate. So if this is your excess, by default, this is your limiting, meaning all of the lead and lead 2 nitrate turned into the lead and lead 2 carbonate. Okay, so they precipitate this out, they find its mass, and then they do stoichiometry to work backwards to find out what concentration the lead 2 nitrate is. So this is a direct proportion. If you get a bunch, a lot, a high number of lead 2 carbonate, it's probably because you had a high concentration of lead 2 nitrate. If you get a small concentration of lead 2 carbonate, it's probably because you had a small concentration of lead 2 nitrate. So they do their analysis and they realize that their precipitate mass was too high. So they do their percent error and they're off by 3%, and it's 3% too high, meaning they got more precipitate than they should have. It's artificially high. So they're trying to find reasons why, their concentration is artificially high, which means their precipitate must be artificially high. They got too much precipitate. So below, what is a reason that they would have gotten too much precipitate and in turn a too high of concentration of lead 2 nitrate? So the first question says that they put it too hot and it composed into two different things. That's not going to affect this precipitate, okay? The next thing says the filter paper allowed some of the precipitate to escape into the liquid. This means they lost precipitate, meaning they should have had less precipitate. If they had less precipitate, the concentration of the lead 2 nitrate would be assumed to also be less because they didn't get as much solid out. So that's the opposite of what this is saying. Not all the liquid and precipitate was transferred to the filter paper. Okay, so again, this is not enough precipitate. So they leave out some precipitate, which will give you an artificially low number of lead 2 nitrate. So that's the opposite, that's not higher. So the answer is D. The precipitate was not rinsed with distilled water after collection. Now, why is it D? Does anybody know what not rinsing it can do? It can cause too high, an artificially high number for precipitate, which would in turn make you assume you had a more concentration of lead 2 nitrate. But why? Well, the impurities, if it's not clean, could add mass to the precipitate. So you always need to rinse and wash the precipitate to get rid of any impurities that are left over, because impurities will contribute to the total mass of this guy, and you don't want them to. So it is the answer D. Any questions about that? Okay. All right. This is where I need you to listen very, very carefully. There are two ways to do this problem. I'm going to show you the long way and the beautiful, most beneficial way, and then I'm going to show you the short way. So this is called solution stoichiometry. So we're going to end up doing, obviously, mole-to-mole ratios. It's going to be based off of a neutralization reaction, which means like an acid and a base. Acids and bases give you salt and water. And we're going to find out the concentration of the acid, given all this. At first glance, this looks like M1V1, M2V2. Okay, I get that. I understand that it looks like that. And there will be a shortcut way kind of like that we can use, but I'm going to show you the true way first. So the first thing you need to do is write out the reaction. So carbonates, so your Tums tablets are these antacid tablets that are made of carbonate. Carbonates are basic, so they help neutralize stomach acid. So they're going to use sodium carbonate. and they're going to react it with hydrochloric acid. How many products do we get?
3.
3. Look, it's a carbonate with acid, remember? So salt, water, and carbon dioxide. So this is my salt, water, carbon dioxide. And I need a 2 here and a 2 here. Okay? Now, if you know the volume and molarity of the base, this guy, and I ask you for molarity about this guy, I'm going to have to eventually do mole to mole ratios because I am jumping around in my chemical reaction. Molarity and volume gets me moles, so 0.100 moles per liter times 0.025 liters is 0.0025 moles of sodium carbonate. Now I can do mole ratios for every 1 mole of sodium carbonate that react. 2 moles of HCl react. So I have 0.005 moles of HCl per molarity is moles per liter. So per 0.0353 liters. So you end up with 0.142 molar HCl. So molarity to volume, stoichiometry for the neutralization reaction, and turn moles and volume into molarity. Remember, molarity equals moles per liter. This is the beautiful, proper way to do this problem. Do I have any questions so far? Okay. If I jump ahead, you will see this equation, which looks kind of like your dilution equation, but you have to consider mole ratios because the dilution isn't a chemical reaction. When we've been doing dilution so far, we've been taking stuff and mixing them with water, meaning they're not reacting, they're just becoming diluted. This equation involves mole ratios because there's a reaction taking place. So you always have to consider how they react relative to one another. Here's the thing, most kids like using this because it's like cheap, easy, fast, but most kids miss the problem when they do it this way because they forget about the reaction and the mole to mole ratios. And unless it's a 1-to-1 ratio, it will mess up your answer. So I will show you this shortcut method. And then I'm going to do it both ways. I'll be doing it both ways throughout the day, okay? Notice that the moles of, this is from your chemical reaction, your mole ratios are on opposite sides of the equation. So this is all of your information for the acid, yet the mole stoichiometry coefficient for base is on that side and the acid is on the base side. So you have to be careful. Okay, so how would you do this? Well, for this problem, it would be, so it's NB, MA, VA, NA, MB, VB. So how many moles of the base did I have? What's my coefficient for my reaction? It's a 1. There's a 1 in front of sodium carbonate. What's the molarity of the base? It's 0.1. What's the, I'm sorry, whoa. Back me up. What is the molarity of the acid? See, I already tripped myself up. I don't know. That's what you're trying to find. How much acid do I have? I have 35.3 milliliters. Okay, what are my moles in front of my acid? Well, there's a 2 in front of the HCl. The molarity of the base is 0.1 molar, and sorry, I ran out of room. The volume of the base is 25. So you'll take and divide both sides by 35.3. Now, this is what you did. you did 0.1 times point, I wrote it in liters, but 0.025. Then you did mole ratios and multiplied by 2, and then you divided by 0.0353. This is the same exact thing we're doing mathematically. This is just a shortcut method, okay? Again, I don't prefer this way, but it is an option. It's not incorrect. It's just most kids will mess this part up. This is not a dilution problem. This is a chemical reaction. However, it works similarly to the dilution problem in terms of this equation. You just have to pay attention to the mole ratios from the reaction. Question so far? Okay. So what volume of 0.1 molar HCl is needed to neutralize 25 milliliters of 0.350 molar sodium hydroxide? So I'm going to do both ways. So you got to write out the reaction. Oops, I'm going to clear this all. NaOH plus HCl makes salt and water. All right, everything in this one is 1 to 1 to 1 to 1 ratio. So 0.350 moles per liter times 0.025 liters. That's going to give me my moles of base. So 0.35 times 0.025 is 0.00875 moles of sodium hydroxide. For every 1 mole of sodium hydroxide that reacts, 1 mole of hydrochloric acid reacts. So you're at 0.0085 moles of HCl per liter, 0.025 liters. Oh, wrong. I'm asking for volume and I gave you molarity in this problem. Ooh, be careful. See, I went too fast. Molarity equals moles per liter. I have moles, it's right here. I have molarity, it's right here. Rearrange and solve for liters. Liters is moles over molarity, right? You multiply both sides by liters, and then you divide by molarity to get liters by itself. So 0.0085 moles divided by 0.100 moles per liter, and you're left with 0.0875. Oops, this is a 75 liters, which is 87.5 milliliters. Okay, so this was the long, beautiful way. Now, before I move on, I'm going to show you the shortcut way, but I want to ask a question. Actually, give me 1 second. Okay, why did we need so much acid to neutralize the base? So I'm going to delete all this. We needed 87.5 milliliters of hydrochloric acid to neutralize only 25 milliliters of base. Why is that? Why did I need so much more acid than I had of base?
Because that's how much the reaction requires.
It is because that's how much the reaction requires, but why? Why did I need so much more acid? Look, I only had 25 milliliters of base, yet I needed 87.5 milliliters of the acid to neutralize it. Why is that? Good job, Andrew. Thank you. It's because, look how concentrated the base is relative to the acid. The base is much more concentrated than the acid, so you're going to end up needing more acid in order to neutralize this higher concentration of a base. Very good job. So let's do the shortcut way. What was the moles of base? Well, there was a 1 in front of sodium hydroxide. The molarity of the acid is 0.1. The volume of the acid is, I don't know. Moles of acid, there's a 1 in front of the HCl. Molarity of the base is 0.350. volume of the base is 25. You rearrange and solve for this, so you divide both sides by 0.1, and you still end up with this number. Oops. Yeah, you still end up with this number. So 0.350 times 25 divided by 0.1, it's still this number. So again, there are two methods for doing this. We have to include this in here because this is an actual chemical reaction. It is not just dilution. Dilution means mixing something with water, which is not a reaction. Okay, so when we do titrations, all that titrations are a lab technique of finding an unknown concentration. So when I say titrations and neutralizations, you can do a neutralization reaction by performing a titration, meaning in one piece of equipment you have an acid, in another one you have a base, and you perform a titration. So the analyte is the substance you're trying to find out about. Usually you're trying to find its concentration. And then the titrant, the thing that you know, is called the standard solution, and you know its concentration. So in order to do this, you have to know the concentration of one of the substances in order to figure out the unknown concentration of the other substance. Now, titrations aren't limited to just acid-base reactions or neutralization reactions. You can actually have reactions that produce a solid and do a titration. You can have what are called redox reactions, which we haven't gotten to yet, but you can do those with titrations. Again, titration is just a laboratory technique for doing different kinds of experiments. And for the sake of the class right now, we're going to do titrations with acids and bases, aka neutralization reactions. All right. Okay, so the equivalence point in a titration is defined as the point where the moles of acid, which is hydrogen ion in this class, and the moles of base, which is hydroxide ion, are equal, okay? Now, for right now, that will be at a neutral pH. For you, what have you always learned that a neutral pH is? What pH number? pH what? It's pH 7 is considered neutral for right now. Now, that is technically not what neutrality is, meaning neutrality is not based on pH. That's what you're used to thinking. By definition, please write this down. By definition, neutrality is when the moles of acid equal the moles of base. That's what it means to be neutral. It's not defined by pH. Now, pH equals 7 is neutral as long as the acid and base are both strong. If they are not, that is not where neutrality occurs. It has a different equivalence point. So you just need to be careful. Equivalence point is not always at pH 7. Perfectly neutral is not always at pH 7. That's what you're used to thinking, but it's not true. Okay, so this is a 6-minute video about how to set up and perform a titration. Yes, you need to understand it and the process. So I'm going to just open it up and we can hang out and watch it together for 6-ish minutes.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, we will be discussing the proper titration technique using the complete single burette assembly kit available from Carolina Biological Supply Company. This is the first in a 2-part video series on titration. The purpose of a titration is to quantitatively determine the concentration of an unknown solution, commonly called the titrand or analyte, by adding a volume of a chemical with a known concentration called the titrant. To mark the endpoint of a titration, an indicator is added to the analyte. Let's review some of the equipment that's needed for a titration. Carolina's complete burette assembly contains the basic equipment to get you started, including a burette, ring stand, and a burette clamp. A burette is a long, narrow, graduated tube used to add titrant. It has a stopcock to regulate the flow of liquid. Notice that the markings on the burette go from lowest at the top to highest at the bottom. The ring stand and burette clamp are used to mount and secure your burette. Other materials you will also need include a small funnel to help you fill the burette, a 125 milliliter Erlenmeyer flask, which works best for titrations. The shape of the flask allows for more vigorous swirling than a beaker or other glassware and minimizes spill hazards. A volumetric pipette and pipette bulb to transfer a known volume of analyte to the flask. A wash bottle filled with deionized water, a beaker or flask of titrant and of analyte, indicator selected for your reaction, a reading card to help read the meniscus, and a sheet of white paper to help visualize the endpoint. To prepare your burette for the titration, it is good laboratory practice to rinse your burette thoroughly with deionized water, then with a small amount of titrant. After each rinse, open the stopcock to allow the liquid to drain out the bottom. If there is a lot of liquid clinging to the walls of the burette, then thoroughly clean your burette and repeat the rinse process. The accuracy of this technique is dependent on the titrant flowing into the flask and not sticking to the walls of the burette. Mount the burette in the clamp, making sure it is positioned vertically, and there is enough room to position your flask underneath the tip. Check to see that the stopcock is in the closed position. Insert the funnel into the top of the burette and fill with titrant almost to the top. Filling exactly to the zero mark is not necessary, but you do need sufficient titrant to complete the reaction. Check the column for air bubbles and gently tap to free them from the side walls. Remove the funnel. Place the Erlenmeyer flask under the tip and open the stopcock to allow a few milliliters of titrant to flow through, releasing any trapped air. Rinse the tip of the burette with water. Empty the liquid into a waste container and thoroughly rinse the flask. It is not necessary to dry the flask. Record your starting volume. It is important to accurately read the volume on the burette. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires two hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little past the endpoint, subtract 5 milliliters from that number to get the amount of titrant that can be safely added before a slower addition is required. As the estimate titration shows, a dark-colored solution indicates an excess of titrant has been added. The desired endpoint is a pale, faintly colored analyte. To reduce the risk of passing the endpoint, slow down the addition of titrant when flashes of color begin to appear in the analyte. Adjust the stopcock to slow the flow of titrant to a drop-wise rate. Continue to swirl the flask with one hand and keep the other hand ready to close the stopcock. When you notice the indicator taking longer to fade, close the stopcock. Rinse the tip of the burette with deionized water and swirl the flask. Record the final volume on the burette. If the analyte remains faintly colored, then you have reached the endpoint. If the analyte is still colorless, then repeat these steps. Add a drop, rinse, swirl, and record until a faint color persists. Typically, titrations are performed in triplicate. Use the average volume of the titrant required to reach the endpoint for any calculations. You now know how to properly perform a titration. Be sure to check out the second video in this series. In that video, we will go over the proper procedure for determining the concentration of an unknown acid solution using a base of known concentration. Carolina has everything you need for your chemistry lab. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right. So, my computer frozen. No, don't do this to me. All right. Okay, so these are going to be some problems, and I'm only going to do 3 of them. I'm not going to do all of them. That you can do using the shortcut method, as long as you know the reaction, where you don't get a calculator. So it's pretty fair game on the multiple choice section. So they give you titrations, they give you molarities and volumes, and they ask you like what the concentration is, the unknown concentration. In order to do that, you have to know the reaction. So I'm going to skip the first one, and I'm going to go just to the second one. NaOH plus HCl makes NaCl plus H2O. So this is a 1-to-1 ratio. So all the molarity or moles of the base is 1. Molarity of the acid is the unknown. Volume of the acid is 25. Moles of acid is 1. Molarity of the base is 0.25. Volume of the base is 50. So you divide both sides by 25. 50 divided by 25 is 2. 2 times 0.25 is 0.5. Now, let's look at this conceptually. You have 0.25 molar base, and you needed 50 milliliters of it to to neutralize only 25 milliliters of acid. So if you needed more base than you did of acid, and they're reacting in a 1-to-1 ratio, it has to mean that the acid was more concentrated. Well, they're more concentrated in direct proportion. If I needed double the base than the acid, then the concentration of the acid must have been double that of the base, and it is. 0.5 is double that of 0.25. So conceptually, you can also see that. Okay, so let's do the next one. Let's look at this conceptually. Let's write out the reaction to make sure they're reacting in a 1-to-1 ratio. And they are. Everything is 1 plus 1 minus 1. Okay, so conceptually, let's look at this before I do the math. So I have 100 milliliters of 0.4 molar to neutralize 200 milliliters of potassium hydroxide. So I needed less nitric acid to neutralize 200 milliliters of potassium hydroxide. If I needed less nitric acid, it must mean the nitric acid is stronger in concentration. Well, how much less did I need of it? I needed half as much. So the concentration is half as much. It's going to be 0.200 molar. But let's do the math. Okay. So let me erase this part. The mole ratios are 1-to-1. Molarity of the acid is 0.4. Volume of the acid is 100. Base is 1. I'm sorry, acid's 1. Molarity of the base, I don't know. Volume is 200. So you divide both sides by 200. 100 divided by 200 is a half. A half times 0.4 is 0.200. Questions so far? Okay.
For when you have more than one number on the what's its name? Sorry.
What's
The equation, not the number equation. Sorry, the
when like a
chemical equation.
mole ratio? Yeah,
When you have more than one number for the ratio, would you put that where the ones are?
Yes. So if one of them's like a 2 and one of them's a 1, that's where they're gonna go. This is like I'm doing the cheating way.
Yeah.
This way.
Yeah, I'm aware. Okay.
Okay.
I'm just making sure.
Yeah, we're gonna actually do one right now. So I
Thank you
think
so
you'll
much.
be able to see, of course. Okay, so this last one with the star next to it has a star next to it because the ratio is not going to be 1-to-1, which makes the problem harder. You have to consider the fact of the ratios because they're reacting. They're not just diluting. So sodium hydroxide is being titrated with, which is mixed with, sulfuric acid till they get to the end point, H2SO4. And we're going to make sodium sulfate and water, which is then going to require a 2 in front of here and a 2 in front of here. All right, so at first glance, you have a certain volume of base, sodium hydroxide, and then you have the same exact volume of acid. So at first glance, you would think, well, if you needed the same amounts of acid and base, then their concentrations are probably the same. Now, that's not going to be true because you actually need double the amount of base than you do of sulfuric acid, because sulfuric acid donates 2 hydrogen ions every time it breaks apart into solution. So I need double the hydroxide ions. So if that's the case, if this concentration has to be higher to make by double than the sulfuric acid, then the concentration of the sulfuric acid is going to be half that of the sodium hydroxide. Now let's do it with the math. So molarity of the acid, that's what I don't know. Volume of the acid is 100. And then moles of base go over here. So 2. There's a 2 right here. That's my base. Equals, so my moles of my acid go over here. This is a 1. Volume of base is 100. Molarity of base is 0.4. So this is, in essence, the hundreds cancel. I'm dividing by 2. Divide by 2. 0.4 divided by 2 is 0.200 molar H2SO4. Now, mathematically, or I guess on the particle level, every time sodium breaks apart, it does this, Na plus and OH minus. The issue is that every time sulfuric acid breaks apart, it does this. It presents 2 hydrogen ions, okay? This is where neutralization is occurring, acid-base. So there's double the hydrogen ions every time you make the reaction with sulfuric acid. So you needed double the hydroxide ion to help neutralize that extra hydrogen ion because sulfuric acid donates 2 of them every time it breaks apart. So that's where this 2 comes from right here. Question so far, right? So like if it's 0.4 molar sodium hydroxide, it's 0.4 molar sodium and 0.4 molar hydroxide. If it's 0.2 molar sulfuric acid, it's 0.2 of this hydrogen and 0.2 of this hydrogen and then 0.2 of the sulfate. Well, combined, that's a total of 0.4 molar hydrogen ion. Any questions on that? Okay, so this is just me showing you that what I just did on the last slide. This is the shortcut method up here, and this is the long method down here. Okay, so in titrations we use indicators. So the one that the guy used in that video was called phenolphthalein, and in a pink solution it's, or in a basic solution it turns pink, and in an acidic solution it turns colorless. So let's have a quick refresher of the pH scale for right now. In general, for the sake of this class, a pH greater than 7 is a base, a pH less than 7 is an acid, and a pH equal to 7 is neutral. And then litmus or pH paper turns red in an acid and blue in a base. Now, we're going to look at some different indicators. So for strong acid and strong base titrations, the equivalence point is at a pH of 7. So can someone give me another indicator besides phenolphthalein? He used phenolphthalein in the video. That's this guy right here. Okay, what's another good indicator that we could probably pick out if our equivalence point is at pH 7 for an acid-base titration. This allows us to visually see the equivalence point. Like hydrochloric acid is colorless, sodium hydroxide is colorless. If you mix them together, they stay colorless. So the only way to like see or visualize an equivalence point, which is where you would stop at your titration, is to have some sort of indicator in there to change color to kind of like signal, oh, you're at the equivalence point. Otherwise, visually, you wouldn't be able to see it. So what's another indicator we could use that changes pH around 7? Or changes color around a pH of 7, excuse me.
Litmus paper.
Okay, litmus paper would be okay, but it's not really going to give you the, it could use neutral, I guess, but what indicator? So pH paper and indicators aren't the same. Indicators are like liquids that you drop in there, so I want to do just indicators. Which of these indicators given would be another good indicator we could use that changes color around a pH of 7? What about bromothymol blue? Look, it's yellow, 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 and then around 7 it turns green, and then it goes to blue, so you'd be looking for a greenish color. That would be a good one. What's another one? So pH 7. Phenol red turns like orangish around pH 7, so that would be another one. Now remember phenolphthalein, that they did not want the solution to be pink. When the solution is pink, you're at actually like a pH of 8. Now they wanted it to be pH of 7. So do you remember what color they were asking for it to actually be in the video? It's generally a faint pink, because faint pink happens around a pH of 7. Very, very, very light or faint pink. And that's where it indicated that you had reached the equivalence point. So if you had gotten dark pink, you went too far with the phenolphthalein indicator. Any questions about indicators so far? Okay. All right, things are going to get very hard. I need you to take very good notes, not just on the math, but on the things that I'm saying, okay? Your homework is to go back in and do all the ice chart problems that you hadn't been able to do now. Someone's not on mute. Can you, everybody make sure you mute yourself? Okay. So, there are 3 things going on in this problem. That's what makes kids confused and tricky. Let's try to identify all 3 things that happen. First of all, a chemical reaction happens. I would like you to at least write out the chemical reaction. Nitric acid is reacting with barium hydroxide. So barium nitrate. Actually, I think I have a bigger slide. Acid, base, salt, water. And then I need to balance. Okay. So there are 3 things that happen in this problem, 3 different things. Can anybody tell me what one thing that happens, what type of problem it is? It's actually 3 types of problems combined into one. Anyone know what one of them is?
Reaction.
Okay, a chemical reaction, yes. So this isn't a dilution. Well, I shouldn't say that. This is an actual chemical reaction, so mole ratios are going to be important. Something else does happen. What happens when you mix the 2 things together? You take barium. Neutralization, yes. So they react and a neutralization occurs. But what else happens? What's your total volume when you mix both of these solutions together? Anybody?
81 milliliters?
81 milliliters. So what's happening at the beginning when you mix them together? Dilution. Okay, so dilution is occurring. So not only are they reacting, they're also being diluted. One more thing also happens. Notice I gave you amounts of both reactants. That makes it what kind of problem? Let's see. Limiting reactant. Thank you. This is a limiting reactant problem. What's the hint? I know amounts of both reactants. Okay, when we have solutions, you need to know concentrations. Now, you don't I know that this is 0.25 molar nitric acid, but the second you mix it with this guy, the total volume changes. So dilution happens. So the first thing, step one, you need to do is if there is a dilution occurring, you need to do the dilution calculations. So write that down. If there is a dilution, you need to do the dilution first. Do the dilution first if there is one. So that's M1V1, M2V2 for both reactants. So I'm going to do it for the nitric acid, and then I'm going to do it for the barium hydroxide. So 0.25, oops, times, what was it, 28 milliliters? Equals a new molarity, dilution. We're not reacting them yet. They're just being diluted. Now the new volume is 81 milliliters. Well, where did I get that from? Well, if you take 28 milliliters of stuff and you mix it with 53 milliliters of stuff, when you add those two numbers together, you get 81 milliliters of stuff. This is before they even react. So you do that calculation. Oops, 28 times 0.25 divided by 81 is 0.0864 molar HNO3. Now you need to do this again, but for barium hydroxide. So the barium hydroxide was 0.32 molar, and you had 53 milliliters of it. So, oops, sorry. 0.32 molar, 53 milliliters. New molarity, total volume, 81 milliliters, equals 0.32 times 53 divided by 81, 0.209. So the nitric acid is the acid, the barium hydroxide is the base. What makes something an acid and a base? I got this question last class, and it was a really good question. So having hydrogen ions, for the sake of right now, makes something an acid, and for the sake of right now, having hydroxide ions makes something a base. Okay? Question so far. So I did the dilutions. That's step one. Do the dilution. Now, here's what you have to be careful of. This is a chemical reaction where there are spectator ions. So this guy's aqueous, it's a solution. This guy's aqueous. Remember, nitrates are always soluble. And this is a liquid. What is the net ionic of this equation? A strong acid and strong base will always have the same exact net ionic equation. Does anybody remember what it is? If you don't, try to figure it out right now. Break everything apart that you can, cancel out your spectator ions, and then determine the net ionic equation. I'll wait a minute. So let's see. Yes, Micah, good job. H plus OH minus make water. This will always be the net ionic equation for any reaction of a strong acid and a strong base. Remember earlier in this chapter, you needed to memorize who your strong acids and strong bases are. So what does that mean for the barium and the nitrate in there? Well, here's the thing. That means the barium and the nitrate are spectator ions, meaning they do not react. They do not participate in the reaction. They float around minding their own business. Spectator ions can become diluted, but they do not react. So I already know the concentration of my barium ion. If I have 0.209 barium hydroxide, I have 0.209 barium ion, because for every one barium hydroxide ion, there's one, or compound, there's one barium ion. I also know my other spectator ion, nitrate. If I have 0.0864 molar nitric acid, I have 0.0864 molar nitrate, because every one nitric acid has one nitrate. Questions about the spectator ions?
So which one of these are considered the spectator ions? Is it the hydrogen and
The barium and the nitrate are spectators.
Okay, thank you so much.
The net ionic are the things that are actually participating in the reaction. The hydrogen is reacting with the hydroxide to make water. This is what neutralization is. Acid right here, base right here, makes water. That's how the acid is being neutralized by the base to make water. That's how neutralization occurs between a strong acid and a strong base. Okay, now I need to erase this. Write this down, my exact words. Ice charts are just an organizational tool for math. Ice charts are just an organizational tool for math. We're going to use ice charts to help organize our limiting reactant problem. Okay? They aren't necessary. You don't have to do them. However, I'm going to do them so I can help you organize all of the math. What we are doing in the ice charts, you already know how to do. This is a limiting reactant problem. How do I know it's a limiting reactant? I have amounts of both reactants. Now, listen very carefully. Because I have molarity and we're used to doing moles, you can do moles in the ice chart. However, I'm going to do molarity in the ice chart. Here's why. The volume of each of these guys now is the same. These numbers correspond to an 81 milliliter solution. So I can use molarity instead of moles, because both of their volumes at this point are the same. Okay, so ice chart, ICE. I stands for initial, C stands for change, and E technically stands for equilibrium, but for right now we're not going to equilibrium, we're going to go to the end of the reaction. So this is how much you have to start off with. This right here, this row right here, this change row, is found using stoichiometry, mole to mole ratio. Okay, and if you take and combine the I and the C, you'll get your answer for the end. So you combine the I and the C, and that makes up what you have at the end. So let's plug the numbers in. What's my initial concentration? Now initial, be careful. I'm not using this 0.25 molar. I know that they give you that initially. I want to use the diluted nitric acid and then react it. So I'm going to use my initial of nitric acid is, let me do a different color, 0.0864 molar. That's my initial concentration of nitric acid once they're diluted. They've not reacted, they've just been diluted. And what's my barium hydroxide? It's 0.209 molar barium hydroxide. Now, how do I know it's a limiting reactant? Well, because I have amounts of both reactants. How do I figure out the limiting reactant? I take my substance and divide by the mole ratios. So this number right here gets divided by 2. This number gets divided by 1, and I pick whoever is the least. This is my limiting reactant. This number is the smallest. Question so far. So now, mathematically, how much of the limiting reactant reacts? This is super important. How much of the limiting reactant reacts? Anybody? All of it. That's the whole point of the limiting reactant. I'm going to lose, so I put a minus here, all of my limiting reactant. That's the whole point. It should all run out. So I shouldn't have any at the end. 0.0864 minus 0.0864 is 0. Theoretically, I should have no nitric acid at the end of this reaction. Which means if I have no nitric acid, who do I have? I have barium hydroxide in excess or left over. How much? Well, I don't know. Do mole ratios. How much of this guy reacts? Well, if 0.0864 of the nitric acid react, for every 2 nitric acids that react, 1 barium hydroxide react. This is not new. This is stoichiometry. We're just using molarity instead of moles. That's the only difference. So I get 0.0864 divided by 2. I'm going to lose 0.0432 molar. That's the outcome of this math right here. This is not new. Then you would take your initial amount. You take how much reacted, and the rest is what's in excess or left over. So 0.209 minus 0.0432 that reacted, and you have, rounded to 3 sig figs, 0.166 molar barium hydroxide in excess. This is excess right here, left over at the end. Questions? Now, if I have 0 of the nitric acid at the end, what's the concentration of hydrogen ion? Well, 0. I don't have any. It ran out. The acid's gone. Now, what's the hydroxide ion concentration? So it's 0.166 molar barium hydroxide, but just remember, when barium hydroxide is in solution, it's this. It's a barium and 2 hydroxides. So this is 0.166, this is 0.166, and this is 0.166. So what's the total? It's 0.166 times 2, right? Because there's 2 hydroxides. So it's 0.332 molar. And then this is the most missed question. Is this solution acidic, basic, or neutral, and why? So here's the issue that kids have with neutralization reactions. You think when you make an acid and a base, it neutralizes and it should be neutral. Well, sure, it should be neutral as long as you have perfect amounts of both reactants. I don't. I ran out of acid before all of my base could react. I have excess barium hydroxide, which is a base. So my solution is actually basic. Did neutralization happen? Yes. Some neutralization happened, but once the nitric acid ran out, I had leftover base sitting in there unreacted, so the solution is actually still basic if there's hydroxide ions floating around in there still. In order to be perfectly neutral, you would have to run out of both reactants perfectly, and I didn't. This is very hard stuff. Do you have any questions? We're going to try another one. I'm probably going to go a little bit over finishing it. You can log off in about 6 minutes or so. I think that's when class is over, to go to your next class, but I'm going to continue it so that I can finish doing the notes for the video lecture. Okay, so next problem, and this is where I'm ending. I give you a solution being made with sodium hydroxide, so that's a base, and I'm doing it in sulfuric acid. and you're going to assume the volume doesn't change upon the addition of the solid. So my first question to you is does this problem involve dilution? Yes or no? Are there any dilutions happening? Is there a change in volume to cause dilution? Yes or no? Anybody?
There's no dilution.
There's no dilution. Now, is there a chemical reaction?
Yes, I think. Yes.
Acid and base is a chemical reaction. So part A asks you to write out the molecular equation, the ionic equation, the complete ionic or gross ionic equation, and the net ionic equations. So let's do that. Sodium hydroxide is reacting, this is a base, with sulfuric acid. Acid, base, salt, water. So let's do that. So this is my molecular equation. So this is aqueous once it's dissolved. This is aqueous. Alkali metals are always soluble. Aqueous, water is a liquid. A, sodium hydroxide, is one of your strong bases. Sulfuric acid is one of your strong bases, meaning instantly, what's the net ionic? H plus OH minus makes water. Watch. 2Na plus 2OH minus plus 2H plus SO4 2 minus makes 2Na plus SO4 2 minus plus, you don't get to rip apart liquids, 2H2O. So my spectator ions are obviously 2 sodiums and a sulfate, and I get 2OH minus and 2H plus is 2 waters. Reduced is, divide everything by 2, this. Question so far? Okay.
For these problems, should we take out usually every number but the hydrogen and the acid?
Well, for right now, yes, because for right now, they're always gonna be a strong acid and strong base for this type of problem. Later on in the year, they won't always be like that, so you can't always do that. But for right now, it's just gonna be H plus and OH minus make water for the sake of class right now, yes.
All right, thank you.
You're welcome. So who are my spectator ions? Sodium, right? And sulfate ion, meaning they're not going to participate in the reaction. They're just going to sit and float around in there. So let's do some math. If I know the mass of sodium hydroxide, what can I get? If I know grams, I can turn it into what? Moles.
Or
moles,
you know,
yep.
like
moles,
volume.
And then you can turn it into molarity because you know what volume container it's going to be in. So let's find the molarity of sodium hydroxide. So, 10.6 grams sodium hydroxide. Sodium hydroxide is 40 grams per mole. So 10.6 divided by 40, 10.6 divided by 40 is 0.265 moles. And it's dissolved in 750 milliliters, which is 0.750 liters. So that's 0.353 molar sodium hydroxide. Right now, you know your sodium ion, right? We know sodium does not react, so whatever its concentration is its concentration here, 0.353 molar. Okay? Now, here's what's interesting. Because dilution did not happen, and why didn't it happen? It's because we didn't mix volumes, okay? Because dilution did not happen, This is my molarity of sulfuric acid. It's 0.750 for sulfuric acid. I didn't have to do M1V1, M2V2 because there was no dilution. So it's 0.750 molar sulfate, right? Because sulfate's not going to react. It's whatever this is. So now I have amounts of both reactants. So because I have amounts of both reactants, it's a limiting reactant neutralization problem. So it's a limiting reactant problem just using an acid and a base. So I'm going to use my ice chart to set up the math. This is just an organizational tool. So I have 0.353 molar sodium hydroxide. Let's see, what color am I going to do? I'm going to do black in here. 0.353 molar of this guy. And I have 0.75 molar of this guy. To figure out your limiting reactant, you divide by the respective coefficient. So you divide this by 2 and you divide this guy by 1. This guy is definitely smaller, so it's my limiting reactant. So how much is consumed of it? All of it. I lose all of it. So I have none left. So 0 molar NaOH. Now, to get this guy, I have to do mole ratios. So if 0.353 molar of the sodium hydroxide react, this is reacting in a 2-to-1 ratio. So 0.353 divided by 2 is 0.17666, whatever. So this is going to be right here. I'm going to erase this real quick. So this is what I just did right here. This is minus, because I'm losing, reactants lose concentration. It's going to react this much, 0.1766666. I'm just going to keep the whole number in my calculator because I'm not finished. So 0.750 to start with, and 0.1766666 of it reacted. So I have 0.573 molar excess sulfuric acid. So how do I find how many? So how do I find how many hydrogen ions? Well, there's double, right? When this breaks apart, it breaks apart into this, 2 hydrogen ions, and a sulfate. So if this is 0.573 and this is 0.573, it's 1.15 molar hydrogen ion and 0 molar hydroxide ion because there's no sodium hydroxide. So if anybody's still in here, it looks like all of you are still in here. Sorry, I know I'm going over. I've just finished. Is this solution acidic, basic, or neutral, and why? Did neutralization happen? Yes. Acid in a base is neutralization. Did perfect neutralization happen? No. I had leftover unreacted acid in there. If there's unreacted acid in there, the solution is still acidic. I didn't complete the full neutralization. I did some neutralization, but not completely. Leftover hydrogen ion, which means acid, gives you an acidic solution. Hydroxides are our base. I don't have any of it, so it still remains an acidic solution. I did not add enough base to fully react all of my acid. Do I have any questions on this? I know this is hard stuff. I'm glad I recorded it. We'll go over these more.